Welcome everybody. Our second lesson in derivatives here, our basics. We're going to talk a little bit more about the derivative as a function, the graph of the derivatives, things like that. We're also going to bring to light a little thing called the power rule, which is a lot more effective way of finding a derivative rather than, well, our friend here, the difference quotient. However, it is good to know the theory behind it, in that the whole idea of limits and whatever are actually like the foundation that leads to stuff like derivatives and integration and some of the major components of calculus. So let's continue. So term I need you to know, differentiation. Quite simply, it means to find the derivative of a function. So if you can find a derivative, that means the function is differentiable. So some notations for you again. Y prime, let me try that again. Y prime, F prime, dy dx, the derivative with respect to x. All those represent different ways of saying to derive or to find a derivative or to differentiate. We got our old friends here. Here's our buddy, the difference quotient. Here's our buddy, the definition of the derivative. Both of them will do what you need to do. They will help you find the slope of a tangent line, which I'm going to designate as f prime of x. Both of these ways will do that. Both of these are really effective tools, but again, yeah, I kind of dig the power rule. Okay, so in this particular equation, I'm asking you to find the derivative, or in this problem, I'm asking you to find the derivative with respect to x of the equation f of x equals x squared plus 1, and use it to find, here's a keyword here, the equation of the tangent line. So if you recall, the equation of a line in in point slope form is y minus y1 equals m, only in this case I want the m to be the slope of the tangent line, and then x minus x1, and the only thing I have is that x coordinate right now. So probably the easiest thing to do is just to find your y coordinate. So again, to do that, to find your y coordinate, I just plug into f of x. So I want f of 2, and f of 2 is going to be, instead of x squared plus 1, 2 squared plus 1, that's 5. So, okay, that's taking on the easy stuff. Now we go and try and find that slope, or that m tan, that dy dx, whatever you want to call it, that f prime. I'm going to actually do it both ways, with definition of derivative and the difference quotient. If I do definition of the derivative, again, that's going to tell me that f prime of x is equal to the limit as x approaches some x initial of f of x minus f of x initial all over x minus x initial. Now let's plug in. I'm interested in finding not f prime of x, but rather f prime of 2, because that is my x value. So I'm going to take the limit as x approaches my x initial value of 2. My f of x right here is that x squared plus 1 minus my f of x initial is my y coordinate, which we just found, that 5, and then x minus our x initial, which was 2. So, all right, I got this. So let's see what we get. So I get the limit as x approaches 2. I have an x squared plus 1 minus 5 is minus 4. Hopefully the little hamsters in your head are running on their wheels right now, and you say, hey, wait a minute. That top is a difference of squares. I can factor it. And even more important than that, you can factor it as a difference of squares, x plus 2 and x minus 2. The x minus 2's in both cases will cancel. leaving you with the limit at 2, which is x plus 2. Replace this x with 2, 2 plus 2. I have the slope of a tangent line of 4. So in other words, if I have a graph of the function y equals x squared plus 1, something like this, basic parabola, parent function, with a 1 unit up vertical shift, at the point 1, 2, comma, let's say 5 is right here, I can tell you that if you draw a tangent line better than I do, and again that passes through our point of tangency at 2, comma 5, this equation is the equation for this line right there. Okay, now let's say, all right, so okay, this definition of derivative thing is not so rough. I can do this. I'm down. I can do it. Let's try the same thing with our difference quotient. Again, the technique you use shouldn't make any difference. The derivative is the derivative at that point. The technique you choose, if it's valid mathematically, should still give me that same answer, or slope of tangent of 4. So let's find out. Our difference quotient says that our f prime, or our slope of the tangent, is our limit as the horizontal displacement h between, our 2 points, x and x initial here. If that's approximately 0, I get the equation f of x plus the horizontal displacement minus f of x all over the horizontal displacement. That's my f prime. So I'm going to take limit, h approaches 0. Okay, this is the part that most people aren't crazy about. It just means I'm going to replace that x with an x plus h, so it's no big deal. So instead of x squared plus 1, it's x plus h squared minus 1, or plus 1. Subtract the original f of x, which is the quantity x squared plus 1, and then it's over h. Again, please make sure you take this whole quantity, put it in parentheses, because we're going to have some distributing to do. So, limit h approaches 0. Again, I'm hoping this is something you can distribute or FOIL in your head. If not, write it out. Do your distributive, have a blast. It gives you x squared plus 2xh plus h squared. Then we got this plus 1. Distribute the negative, I get minus x squared minus 1 all over h. X squareds are toast. 1s are toast. I get limit. H approaches 0. 2xh plus h squared all over h. Okay, again, now if I do direct substitution here, since every term on top and bottom has an h and h approaches 0, it's going to give you that implied 0 over 0 or indeterminate form, which basically means I have no earthly clue what the limit is, or what the slope of the tangent is. To deal with that whole deal with the 0 over 0 indeterminate form, I'm going to actually factor an h out on the top. That's 2x plus h all over h. Now those h's cancel, leaving me with 2x plus h, and h approaches 0, so that gives me 2x plus 0. In other words, I get f prime of x is 2x. But like we did in the other one, I'm not really concerned with f prime of x. I want f prime of 2, which is 2 times 2. Still 4 in my book, people. So choose your poison. That'll work fine. Again, I will show you the power rule, and it's way easier to get to 2x than that, but a little theory is not going to hurt you none here. Okay, so let's talk differentiability. I already talked about differentiate, meant to define the derivative. Differentiability means Does it have a derivative? Can I do it? Can I actually derive this thing? So it is possible that a limit that defines a derivative of a function may not exist at certain points in the exam. When that occurs, the derivative at that point is undefined, or you could say it is not differentiable at whatever point that is. If the derivative does exist at a point, like x initial, whatever it might be, then we say it is differentiable. So in general, a function is differentiable at a point if the graph has a unique tangent line at that point. We'll get to that in a minute here. In other words, to be differentiable means that I can find its derivative. Now, a couple of things that will make a function not differentiable. First of which, corner points is what I like to refer to them as. I've also heard them referred to as sharp turns, whichever you prefer. This is a corner point right there. That's where I have two straight lines, and they intersect. This one has a negative slope. This one has a positive slope, and they're not equal. So let's go a little bit more in depth on this. If a function is continuous, hopefully you remember the three conditions for continuity. Number one, that the limit as x approaches some constant c of f of x must be defined or must exist. F of c, there has to be a point there, must also exist. And lastly, that limit as x approaches c of f of x must equal f of that c. That's to be continuous. And I will tell you, in order to derive or to differentiate, continuity is needed. So if anyone ever tells you that a function is differentiable, I will guarantee that it is also continuous. Without continuity, you cannot have differentiability. So that's one condition. Secondly, now let's talk about the derivative itself. Now, that's to be continuous. Does the function is it continuous? To actually have a derivative, I'm not worried about does the limit at x approaches c of f exist? I want the limit at f prime to exist. I need f prime of c to exist, and I need them to be the same. So here's what I'm talking about in this condition right here. So in addition to being continuous, I need the limit of the prime to exist. Now remember, f prime, that was a really ugly prime. F prime represents the slope of the tangent. So I'm going to go ahead and find the slope of the tangent here. And that's a negative, some kind of a constant, whatever that might be. -1, -2, whatever. That would be my limit as x approaches, let's see, this value is at c here, of f prime of x from the left. So that gives me some positive number over here. I'm sorry, some negative number, excuse me. And then if I were to take the limit as x approaches c from the right, not of f, but of f prime, remember f prime is the slope, that gives me some positive number or some positive slope. So is this negative slope equal to that positive slope? I don't think so. So since the limit at f prime does not exist, this corner point, it doesn't work for me. Another way you can think of it is like this. Again, previously in the notes I talked about to be differentiable, it required a unique tangent line at a point. I could draw like this. I could draw a line like that. Say, if it touched, that's a tangent, that's a tangent, that's a tangent. I could draw a whole boatload of tangents, which basically gets rid of the whole uniqueness part of it. So corner points are bad. Same kind of logic with a cusp. A cusp is a lot like a sharp turn, only it's more of a curved graph, something like that. I don't know if you want to think of it like a bird or something flying. Forgive my artistry, but yeah. And then the other thing is points of vertical tangency. If I have a vertical line, that is also not differentiable. You say, well, why not? If you go back to your algebra class, when you talked about this, we know that the slope of a tangent of a vertical line was probably, you learned that it was undefined. So if that means the slope is undefined, and the slope is another way to say f prime, or the slope of the tangent, if the slope is undefined, that makes f prime undefined, which makes it not able to be differentiated, so not differentiability. And then this kind of puts them in different words in case of my confusion in my confusing you. Okay, let's take a look at a couple things. Now, I went through how to find like f prime of 2 in that first example, you know, with the f of x is x squared plus 1 and all that. Real easy to do using difference quotient, definition derivative, or later on when we do the power rule. Really easy to do that by hand by plugging in. Now, on a graph, how do we do this? Well, I mean, understand that f prime represents the slope of a tangent. So if I want to find f prime of 2, basically what I'm looking for is the slope of the tangent line of f of x, which is this graph right here, at x equals -2. Same deal here, only at different locations. So to do it, here's what I recommend. Draw a tangent line on your graph. Again, I'm not an artist, nor do I expect a perfectly accurate tangent graph on here. And then do your rise over run. So again, since my artistic abilities are lacking to a great deal of extent, I actually used a computer and drew something a little nicer here. So what I did was I went here and we're concerned with the point where x is -2 right here. And I drew a tangent line, and it is a horizontal line, and a horizontal line has a slope of 0, and yes, it is that easy. A little tougher when we get here, f prime at -1. Here's your -1. Let me see about changing some colors here and not doing that again. Okay, so what I did was, again, at this point, -1, I did my best to create a tangent line. So this red line is tangent to this blue or purple, whatever f of x curve there. And I'm just going to, once I get it drawn, I see that that goes up 2 and over 1. And the last time I checked, if I'm doing a rise over a run and it goes up 2 and over 1, that slopes 2. Now again, I put is approximately 2 because, you know, you're constructing that tangent line. You may not construct the perfect tangent line. So it's okay to say that that's approximately. Same deal here. F prime at 2. Here's when x equals 2. Again, I draw like a rough rise over run here, a tangent line. And I see this goes down about 1/2. So it goes down 1/2 and over 1. So down 1/2 means I get a slope of -1/2 over 1 and -1/2 over 1. Considering how well or how poorly I draw my line, I get a slope of a tangent of about -1/2. And again, if you say, well, I got like -1/3 or something, okay, I'll spot you a little bit. Where I would have a problem, say, I got a slope that's +3. No, number one, it's way too steep. And number two, you need to have the sign right. So, okay. Here's where it gets fun. A really necessary skill you need to have on your AP test, or just, it's good just to know like about curve sketching and stuff. Maybe you're in a physics class, you've got a position, velocity, acceleration graph, or so you got a position graph, you're trying to graph what acceleration looks like, or even going backwards like from, you know, a velocity graph, or maybe you got an acceleration graph and you want to go backwards to see what your velocity graph would look like. That's kind of the scale I'm going to show you, just graphing from the sense of a derivative. And yeah, in your physics class, when you're drawing a going from a position graph to a velocity graph, you're actually doing derivatives. And we'll get more into that later, how that the position of a function, I'm sorry, the velocity of a function is actually the derivative of its position. So we'll get into that a little bit here. Now, to do this, the first thing I do is I'm looking at this graph right here. Again, these are graphs of an initial functions f. Right there, I see a corner point. That tells me that f prime does not exist at one location. Say it's like at -1, -2, something like that. So I'm going to go look at the graphs, the capital graphs, which are graphs of f primes, and I'm going to try to find one graph that's undefined at this one point, a little bit left of the y-axis, and I've just found it. Now you might say, okay, explain like why it's like the horizontal lines are, what's you know, the genesis of this, what's going down here. Okay, so this, don't worry about that it's horizontal. See, basically the slope of your graph of f of x is the y value of f prime. I'll explain that here in just a second. So like if I'm looking at this, let's say, okay, this got a slope of like a positive something. Let's say it's like +1 or something like that. What that means, my slope will have a constant y value of like that +1 or whatever it might be. Here, after the undefined corner point here, or a sharp turn, this has a slope of 0, which means f prime will have a y value of 0. So the slope of f is the y value of f prime. That's something I use that maybe helps you a little bit. So I know this first one matches up with capital letter D. Next one I see a whole boatload of corner points, which means I am looking for some graph that is undefined in a whole lot of places. Wish granted. Undefined here, so that's 1, 2, 3, 4, 5 places. There we go. So capital F belongs to you. So anything else that looks undefined? Well, here it looks kind of like a cusp, but I think this is actually a vertical asymptote. Either way, the function is not continuous at x equals 0 here, so that's going to be undefined. So I'm looking for something that does not have a derivative at 0. This one does not. So I know this belongs to C. Now let's talk about the slopes here. Again, here I have a really small negative slope. It gets bigger, and then it gets, oops, sorry, negative here. And then I get a really big negative slope. Then here I have a really strong or steep positive, mild positive, and then a very small positive, which is what this does. Starts off very small negative y value, medium y value, big honking negative y value, big x value after the undefined, medium y value, I'm sorry, and then a smaller. So that's 3 of them down. Okay, the next one, again, this is just based on my experiences of doing these. Next thing I look at, let me go back to that red for just a second here. I think I'm gonna, nope, I don't want to do that. Let me try that one more time. All right, so here what I see all of these slopes are all positive. So basically what I'm looking for, since all of these slopes are positive, I'm looking for a graph. Remember, the slope of f is the y value of f prime. So I'm looking for an f prime graph where none of the points are below the x-axis. We have a winner there. Again, we have a small positive value, a bigger positive value, and then a smaller positive value. And that was A, I believe. So a small positive slope, a bigger positive slope, and then back to a small one. Okay, these last two. First thing I notice, there's no undefines. I see this. Those are referred to as horizontal tangents. They have a slope of 0. Okay, fair enough. Slope of 0. Again, slope of f is the y value of f prime. So I'm going to go look for things that have a 0 here. Okay, they both do. That didn't help. It could, it just didn't happen to in this point. Here's the other thing. Look at this slope right here. It starts off really steep positive, whereas this one starts off almost 0, but actually it's like a really small positive. So the one that matches up with C is going to start off with a very small y value, but above the x-axis. This one's going to be way the heck above the x-axis. So here's the one way above the x-axis right here. Its y value is way up there. So E is going to match up with this one. And then if you know your alphabet, A, B is going to match here. I did in your Schoology folders put these graphs on one sheet like a PDF so you can play with them too. And if you want to check, you're trying it on your own, you want to see how you're doing, there you go. Okay, I'm going to go ahead and stop this video and then I'll pick up with part 2. We'll talk about the power rule and some basic rules of differentiation, and this is part 1.